Chawla presenting Physics 2 Lab 4 on circuits and capacitors. So the purpose of this lab is to explore the concepts of circuits and capacitors using the principles of energy conservation, such as the loop rule and current conservation, to predict the behaviors of circuits containing resistors in series and parallel using multimeters, and to examine the behavior of ohmic resistors and capacitors. So some key concepts and equations. So the node rule, which is that current flowing in is equal to current flowing out. The loop rule, which is a potential difference around a complete circuit loop equals 0. Ohm's law, which is that voltage equals current times resistance. And capacitance, which is that capacitance equals charge divided by voltage. So here's like a condensed version of the procedure for part 1. And then here are the measurements for the potential differences. So as you can see, it increases from A to B. It does not change from B to C. Decreases by about -1 volt from C to D. Does not change from D to E. From E to F, it changes by about -2 volts. And then it's steady at 0 from F to G and G to H. So as we can see, 3 minus 0.96 minus 2.04 is equal to 0. So the total around the entire loop was 0, which is what we were expecting because of the loop rule. So here are like the key measurements for part 1. So in the initial circuit, current was 0.02 amps. When we reversed the ammeter, it was -0.02 amps, which is what we expected. And because as we can see, like 3 volts divided by 147 ohms is 0.02 amps. And for the open circuit, the voltage was 3 volts, and we were expecting 3 volts because there's infinite resistance and no current because it's an open circuit. And then when we added the ammeter, we got 0.06 amps, which is caused by a decrease in resistance, so that causes an increase in current. And then the key resistance of each component, so 0.96 divided by 0.02 gave us 48 ohms. And then for the 100 ohm resistor, we got 2.04 divided by 0.02, which is 102 ohms. And then 0 for the wire and ammeter. So we were expecting 147 ohms, but we got 150, which is probably just because of a rounding error in the simulation. And what we got was what we expected, because we expected basically 0 resistance in the wires and ammeters, and about 47 and about 100 ohms of resistance in those two resistors. So here's the condensed procedure for part 2. And some key measurements and observations from part 2 is that when charging, the maximum current is at the initial point and there's no current when the capacitor is charged. So the times that it took to charge the 10 ohm was about 10 seconds and the 20 ohm was about 19 seconds. And then for discharging, the maximum current was at the initial point and there was no current when the capacitor discharged, and current was going in the opposite direction as compared to when it was charging. So times were about 14 seconds for 10 ohms and 28 seconds for 20 ohms. Okay, here's the condensed procedure for part 3. And here are the key equations that I used to calculate RC. So we see that B capacitor plus V resistor is supposed to equal 0. Q divided by C minus IR is supposed to equal to 0. And then ultimately we get that ln of delta V over delta V naught equals -2 over RC. So that'll basically be the slope of the graph, which is equal to -1 over RC. So my slope was -0.137, so my RC was 7.3 seconds. So for these what if questions, if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated one, it would have had resistance, even if it was pretty minimal. So the resistance would be higher and the current would be lower, just because in real life, it couldn't not have resistance. And if we were doing the lab in real life and used a real battery to charge a real capacitor with no resistor in the current, how quickly would the ideal model predict the capacitor to reach full charge, and would this happen in real life? So ideally, the capacitor is instantly charged if there's, just those two components, but in real life, it would take time because, the wire and stuff would have slight resistance. So in real life, the time measured would be greater. Thank you.